Thank you for joining us today. My name is Marcus Weber, and I will be the moderator for today's webinar. I am the Technology and Execution Council Chair in Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success. Every one of the Innovation Builders team and the speakers on this call are remote working parents and grandparents, and we applaud their ability to find time to share their knowledge in addition to serving their clients, while juggling the intersection of their career and home lives. As with the other webinars, this will be a technical presentation intended mainly for machinery and structural engineers who are interested in knowing more about mechanical and structural considerations when working with machinery modules. We have two Fluor Senior Fellows today with us on the call. Our first speaker is Nitin Gaisis. Nitin is a Fluor Senior Fellow with expertise in rotating equipment. He has 38 years of experience in turbo machinery with expertise in specification development and selection, troubleshooting, rotodynamic reviews, and vibration analysis of rotating equipment. Prior to joining Fluor, he worked as a machinery reliability engineer at Petrochemicals, a SABIC affiliate in Jebel, Saudi Arabia. Nitin has received a Master of Engineering degree from the University of Bombay and is a registered professional engineer in the provinces of Alberta and British Columbia in Canada. He has contributed to the development of API standards and process industry practices for many years and presently holds positions in API as the chairman of API 612, which is the Special Purpose Steam Turbine Standard, and as the chairman of API 672, which is the Packaged Integrally Geared Centrifugally Driven Air Compressors Standard, and is a member of Subcommittee on Mechanical Equipment. He is also a member of the ASME and a member of the PIP Machinery Functional Team. Nitin has authored several papers which are published in leading international magazines and appear in conference proceedings as well. He holds U.S. patent related to machinery modularization. Joining Nitin is a Fluor Senior Fellow, Bill Bounds. Bill is currently enjoying his retirement, but still continues to do structural engineering, which is his passion, under a consulting agreement with Fluor. He has expertise specifically around modularization, foundations for vibrating equipment, and blast-resistant designs. His experience includes 46 years at Fluor in the Civil Structural Department, 16 years of module design experience, and over 30 years of vibration analysis experience. He has engineering degrees from the University of Oklahoma and University of Houston. He is also a professional engineer registered in Texas, Louisiana, and New Hampshire. Bill is a member of the American Society of Civil Engineers and former member of the American Concrete Institute. This includes serving as a member and past chair of ACI 351, which is the Foundation for Equipment and Machinery. Bill has authored papers and presentations on module design and support for vibratory equipment. With that, Nitin, please unmute your line to begin.
Thank you, Marcus, and good morning or good afternoon to all participants, depending on where you are. Modularized projects in this decade have focused on optimizing the layout of facilities and moving a significant portion of site work to module yards to reduce field labor costs. Not only static equipment, but also dynamic and positive displacement type machines are now increasingly considered in the scope of modularization. We'll start off with the session objective. The main purpose of our discussion is to help realize the key benefits of equipment modularization, know the types of modules, pursue feasibility of modularization, understand the technical features of machinery modules, and understand the technical requirements, methods, and principles used in the design of machinery module structures. The material presented in this webinar is specific to onshore modules. Offshore machinery modules and modularization execution strategy are outside of the context of this webinar and excluded. We'll begin by defining module. A module consists of transportable pre-assembly or process plant components. It is designed to minimize site installation and commissioning activities. A modularized program has several advantages over the conventional stick-built design approach. These advantages fall into three categories: cost, schedule, and safety and quality. We will go over each one of them, but before we do so, it is prudent to bring to your attention that a modularization plan or program addresses module types, embedded versus elevated, approach by equipment type, size and weight limits, power distribution and control system, and material sourcing strategy. It is important to note that modularization drives the plot layout, not the layout drives modularization. Let's now see the cost-related benefits of modularization. It reduces labor cost by shifting labor hours from high-cost job sites to lower-cost modulars. The reduction is due to the differential between field and shop fabrication hourly rates. This is especially significant for remote locations and other locations where local labor costs are high. It reduces net material quantities due to the use of a more concentrated module layout. Quantities of concrete, pipe, and cabling are lower. Quantities of structural steel are higher. It reduces site indirect costs. Example, scaffolding quantities and durations. It reduces equipment grouting requirements. And it relocates underground process drainage piping to above ground shop installation, which reduces site underground work. Now let us see the schedule related advantages of modularization. They are: it facilitates parallel execution of fabrication and assembly. It maximizes shop work to reduce weather impacts on productivity by moving large volume of site work to module shop and provides schedule certainty. And it allows accelerated construction schedule and makes it possible to advance plant commissioning and startup. And now we will review the quality and safety related benefits of modularization. These are: it improves quality of workmanship due to more controlled production environment. It enables sound and safe engineering practices in the design and layout to be duplicated in future modularization programs. At the same time, provide flexibility to optimize space and equipment arrangements to address issues such as transmission of vibration from one machine to other machines that share the same structure. It reduces material congestion and movement at construction site. It minimizes safety risks associated with elevated work and stacking labor. Fluor and our partners work closely with clients to understand their health, safety, and environment and human factor engineering requirements. Our cumulative knowledge and design experience, together with our clients' operational experience, provides valuable inputs to modularization conceptual studies. Typically, a modularized project results in 15% reduction in capital cost, achievable by shifting 25% to 30% of site work to module shop or modulars, and 25% less time for cycle completion from start to install through pre-work and on-module inspection, checks, and testing. Many activities are performed on the module. For example, hydrostatic testing of on-module piping, followed by cleaning, flushing, and dewatering. Electrical insulation checks, verification of tagging and cabling, and functional testing of electrical installations. We have just now realized the cost, schedule, and quality and safety related benefits of modularization. Now let us talk about the machinery models in the context of this slide. Many small and large rotating and reciprocating machinery packages are mounted on steel structures in the highly modularized facilities. Several factors help determine the type and the scope of machinery strings that can be modularized. Aspects such as the module size and the weight, construction and testing capabilities of modular or module shop, proximity of modular to the shipping port, site-specific transportation limits, clearance requirements that are dictated by operations, maintenance, and human factors, and benefit to cost analysis. All of them are essential to decide the type and the scope of machinery strings that can be installed on transportable steel structures. We in Fluor complete this assessment or analysis on every project that has machinery modularization as one of its significant drivers. For complex machineries such as centrifugal compressors, expanders, and turbines, we collaborate with equipment vendors and utilize our combined expertise to develop solutions. The concept of machinery modularization begins with a study to evaluate its practicability or suitability. Usually, the prime drivers for model concept study are health, safety, and environment, human factors engineering, long-term reliability of the equipment, operability and maintainability, and cost and schedule. On almost every modularized project, the practicality of machinery modularization is assessed during scope definition phase to validate if it can be developed and accepted for implementation. A design that is not only schedule and cost effective, but also does not compromise safety, operability, and maintainability will likely turn into a successful model project. The scope of the study for machinery models should include site-specific and model-specific considerations that we will discuss now. The site-specific considerations are local and national or federal environmental regulations and standards, environmental conditions at site, including minimum, maximum temperatures and effects of wind, ice, snow, and rain, potential for release of hydrocarbons, and emissions from process and on-model equipment, noise generated by machinery, and contribution from the surrounding auxiliary equipment, noise mitigation, ease of access for operations and maintenance, and inspection and testing of on-model equipment. And now I will discuss the model-specific requirements or considerations shown on this slide. These are safe exit or evacuation paths in case of emergency, clearance space for inspection openings, pull-out lanes, and component removal, available overhead room, projections that restrict access, walkways, ladders, platforms, and railings to reach areas that require frequent inspection, adjustments, recording, or maintenance, on-module lighting and utility stations, material handling and movement, on-module and off-module, preliminary operability and maintainability reviews, module plot size optimization to address needs for laydown space, and extended travel of on-module bridge crane to cover the drop-down area without constraints. Even though not listed here, several additional factors are also evaluated in the machinery model concept study. The precursor to determine model weight and size is the initial static analysis that is followed by dynamic analysis of model structure, and it includes ocean transportation loads if applicable. Let us now discuss the types of modules based on their relative sizes, but primarily the weight. The size of a module determines how much can be installed and how the module will be transported. Modules can be designed as small or large or very large modules. Small modules are complete components of plants and can be transported by road or rail. Typically, small modules are complete packaged units that can be placed on prepared foundations and then connected to the adjoining modules. In most cases, they require minimum pre-commissioning activities. Small modules weigh less than 100 tons and are truckable and easily liftable. Large modules weigh between 100 and 600 tons. They are liftable and require special road trailers. The upper limit on weight of large modules is set by lift achievable at site using conventional rigging methods. Very large modules weigh in excess of 600 tons. In today's world-scale ethylene and oil and gas facilities, module dry weights can be up to 10,000 tons. These modules necessitate special or non-conventional lifting, jacking, and transportation methods. Transportation of very large modules is often by barge or heavy transport vessel and usually involves use of self-propelled modular transporter (SPMTs) to bring the module to its final location and set it in place. The factors mentioned on this slide reflect a distinctive characteristic of machinery models. It is the arrangement of the equipment string. Small modules have a single deck, and some other models include a single deck and a mezzanine floor for the auxiliary equipment. Depending on the specific layout, one machinery string may be installed on a dedicated module, or two strings in the same service may be installed in longitudinal or transverse direction on the module floor. For modules that do not have a roof, air-cooled heat exchangers for lube oil may be integrated with module and mounted on top. Elevated modules allow vertically down-oriented process nozzles on compressor casings. This results in unobstructed travel of the overhead bridge crane and is usually the preferred arrangement. In multi-body centrifugal compressor strings, the radially split high-pressure casing is located outboard of the low-pressure and medium-pressure axially split casings to permit removal of the inner bundle assembly. Accordingly, the laydown area is set on this end of the model. We have presented an example of modularized gas turbine-driven centrifugal compressor train on this slide. A large module for rotating equipment train, such as a gas turbine-driven compressor, typically has an elevated structure, partial or fully enclosed sidewalls, a removable roof, and surrounding auxiliaries. Bridge crane and jeep crane are provided to facilitate maintenance and handling. Such a module is significantly complex and scope intensive in comparison to a module for an electric motor-driven compressor. This is because many auxiliaries for gas turbine and compressor are also installed on the module. For example, inlet air filter house and ducting, gas turbine exhaust duct and expansion joint, gas turbine enclosure ventilation ducts, hydraulic starting system, fire extinguishing system, dry gas seal support system, and so on. Here is a 3D image of a modularized pump unit. Dedicated pump modules typically have several pumps in different services installed on its floor. Multiple units are strategically located based on assessment of their dynamic behavior, operating and maintenance access requirements, and human factor design aspects. Taller vertical inline pump units have reduced headroom for maintenance. Their total installed height is checked against elevation of the first deck on the module from the module's floor. The other types of structural steel mounted equipment, such as positive displacement blowers, centrifugal fans, and rotary screw compressors, are usually part of process or packaged equipment models. A highly integrated machinery module project, such as the one in this picture, involves breakdown of activities associated with several systems and components. At a higher level, this breakdown identifies responsibilities and locations, such as in module yard or at job site, for all major scope of work and scope of supply items, including shipped loose parts or assemblies. Obviously, the intent of this effort is to avoid assumptions that can lead to omitted scope and potential delays. The scope planning should be completed to finalize all interfaces between the module and the balance of plant, and its timing should coincide with the approval of modularization concept. The most significant activities on the modularization scope responsibility document are identified on this slide. Please take a moment to become aware. Other equally important tasks and functions on this document should include scope of supply for machinery string and its auxiliary systems, electrical work, instruments and controls, heat tracing, electrical grounding, mechanical and piping activities, including insulation and winterization if applicable, verification of construction completion, commissioning and on-module testing, for example, continuity checks, hydro testing, flushing, instrument calibration, and lastly, module transportation from the modular or module shop to its final location. Now that we have reviewed the major scope items, let us discuss the details of machinery module's steel structure. I will turn the presentation over to Bill for this section.
Thank you, Nitin. First, I would like to note that structural steel is significant in that it can make up approximately 50% of the module's weight. Weight can have a significant impact to the total cost of module transport. A module's permanent steel structure includes machinery support beams, main trusses, and deck plate girders that contribute to module stability and integrity. For machinery integrity, welded connections are preferred. Other major structural components, as shown on the slide, include elements that are added or removed during transport, such as grillage, or framework between the permanent steel and C-fastening. C-fastening, steel that connects the module to the vessel deck. Internal C-fastening, to protect module interior items during transport. Ship loose or site installed components, for example, external stairs, lightning rods, and module mounting pads. Some early structural decisions are needed, which include welded or bolted connections. This choice is closely associated with the coating choice because welding over galvanizing is a worker health issue. Bolted connections are physically larger and potentially subjected to joint slippage. Painted or galvanized steel. Painting is preferred by many module fabrication yards that are also shipyards because fabrication, painting, and erection can all take place within the yard. Galvanized steel is often required by clients for project sites where corrosion is a more significant long-term concern. Many U.S. Gulf Coast projects use galvanizing and therefore bolted connections. Buried or elevated base frames. This is also a fundamental layout issue. Elevated base frames are more common due to simpler module setting requirements. Buried frames have more flexible egress alternatives and eliminate the need for operators to climb to the first level of equipment. Rigid or flexible framing. This is determined by the relative amount of bracing to be used. Modules may need to be rigid for crane lifts or to overcome transportation issues. Warehouse or mill order. In some global locations, quality is more assured by avoiding warehouse material. Structural loading has significant additional considerations for modules. Loading can be categorized as either transportation loads or site loads. Transportation loads include transport empty weight, and this could be different than the site empty weight. Stowage. These are extra items that might be transported on or within a module. Wind, as determined specifically for transport conditions. Ocean wave loading. These are acceleration inertia forces due to marine vessel motions. Marine vessel hog and sag. This is flexing or bending of the deck due to waves and weight distribution. Vehicle acceleration and road slope. This applies to land transportation by truck or SPMT. Site loads, listed on the slide, are the same as for conventional stick-built structures. However, there are several aspects of particular significance to module design. Climactic thermal. These are forces due to temperature-induced expansion and contraction. These forces are more significant for modules with large base frames relatively close to grade. Further complexities can result for Arctic modules that may have portions of the structure fully exposed to exterior temperatures or fully climate controlled or just heated. Material handling. Condensed module layouts tend to make material handling more complex. This means that monorails, pad eyes, wheel carts, and drop zones can impact the layout and structural design. Machine vibration. This is significant because the mass on a typical steel structure is less than the mass provided by a conventional concrete foundation. For analysis and design, there are several fundamental considerations of significance to modules. For site conditions, the design needs to meet the legally established building code. However, the building code rarely applies to module transport. For transportation conditions, the project specification will apply, or if not available, we can follow an approved internal guideline or an industry standard, such as API, DNVGL, or ISO. Varied support or boundary conditions are unique to module transportation design. Marine transportation, SPMT transportation, crane lifts, and site conditions each have different support conditions. Fluor has established a technique to use a single analysis model that enables boundary conditions to be easily switched. Transportation fatigue can be significant for longer marine transportation routes. This mostly affects structural connections. Weight and center of gravity envelopes are commonly used for the design of offshore modules and typically are applied to onshore modules. In addition, the design weights used must correspond to the module weight report. Based on experience from past projects, Fluor has prepared a design margin document on this subject. A static analysis is used for all types of structures, including modules. Static loads are almost always used, including some loads that are dynamic in nature. Transportation loads include a combination of marine transportation, land transportation, and crane lifts. Exact combinations and requirements can vary widely from one project to another. For large and very large modules, marine loading is normally determined by a naval architect. Site loads are analyzed in the same manner as a stick-built structure. Seismic forces are typically based on the equivalent lateral force method or a response spectrum analysis, and then applied statically to the analysis model. Fluor has developed several program spreadsheets to automate and facilitate transportation and site loading calculations. The dynamics of vibratory machines is significant in that preconceived assumptions or a lack of experience with modularization can drive decisions on what equipment is or is not to be modularized. Thus, aspects of this subject are covered on the next several slides. Centrifugal machines are the most common type. The dynamic load originates from an imperfect shaft-rotor alignment, which slowly increases over time during operation. If the shaft and rotor are perfectly aligned, then there will be no vibration. Reciprocating machines are not quite as common. The dynamic load originates from the inertia of components moving through a designed range of motion. These forces occur whenever the machine is operating. Less common machinery types are impact-type machines and reactors subjected to random vibrations. Now let us look at the fundamental considerations in a dynamic structural analysis. Mass and center of gravity for the structure are computed based on the analysis model. For the machine, this information should be requested from the machine supplier. For the structure, stiffness is computed based on the analysis model. Damping is applied using a low-end value of a damping ratio. For the foundation, stiffness and damping are determined based on the geotechnical report and proposed foundation. Rigidity of machine support is applicable to any situation, but becomes significant when supporting on steel framing. Support rigidity is needed to maintain shaft alignment and to allow cancellation of internal machine forces. As a cautionary note, the rigidity of the machine itself is commonly oversimplified and can contrast with the supplier's rotor dynamic analysis. I've seen many structural analysis models that assume the machine is completely rigid. This can be an invalid assumption, especially for larger machines. For example, in the analysis diagram shown, the machine shaft is not rigidly connected and it will not restrain movement of the bearing supports. Machine skids should also be carefully considered and modeled accordingly. Specification criteria is provided through one or more of the following in order of priority. First, from the machine supplier. Second, from the client or project specification, but this can govern if it is more restrictive. Third, from Fluor's internal guidelines, or finally from a recognized publication such as API RP 686 or PIP STC 0015. The determination of the dynamic force depends on the machinery type. A centrifugal machine diagram is shown on the left. As previously mentioned, this force originates from an imperfect shaft-rotor alignment, which creates an unbalanced rotating mass. If not provided by the machine supplier, centrifugal forces can be computed from rotor balancing criteria, plus an allowance for wear and tear. Rotor balance grades are available in ISO 21940. Reciprocating machine forces are indicated on the right. The dynamic force originates from the inertia of components moving through a designed range of rotating or back and forth motion. These forces occur whenever the machine is operating. One cautionary note is that net forces are usually provided based on a cancellation between the shaft and cylinder head. For this purpose, the supporting structure may be needed to help maintain sufficient rigidity, especially for larger machines. Reciprocating forces need to be determined and supplied by the machine supplier. The dynamic analysis itself consists of using the mass, stiffness, damping, and dynamic load to compute deflections or amplitudes. This is a service level analysis, and realistic values or a range of realistic values are used. Except for damping, conservative values are not desired. The most common analysis approach is a modal time history analysis. This approach uses a modal analysis to determine natural frequencies, followed by a time history numerical analysis to determine deflections. Considerable caution is needed in determining the parameters, for example, number of modes, time step, and analysis duration. For large analysis models and high-speed machines, the analysis can be time-consuming, such as a matter of hours. A steady-state analysis is a direct calculation of deflections based on harmonic force. Resonance can be evaluated by calculating across a range of machine speeds. Compared to a modal time history, the parameters are relatively simple, just force and frequency. This approach is quite fast for a single frequency, such as a matter of minutes, but it will be slower if analyzing a range of machine speeds. Acceptance criteria is the same as used for conventional stick-built installations. The acceptance checks I will discuss are for resonance, machine tolerance, and human tolerance. A resonance check is made to avoid the possibility of large amplitudes due to variations in input properties. Resonance is compared using a frequency ratio, which is the machine frequency divided by the natural frequency. The natural frequency is obtained as part of the dynamic analysis. The chart shows the frequency ratio on the horizontal axis versus amplitude on the vertical axis for several dark line values of damping. A frequency ratio of 1, when the natural frequency equals the machine speed, plus a low damping ratio results in the sharp peak shown in the middle. The design intent is to avoid resonant frequencies within the specified resonant range, as indicated in red. Depending on the applicable specification, the specified resonant range is generally plus or minus 20 to 40% of the machine speed. Complicating factors include variable speed operation. However, the amplitude of response is the primary concern. The next acceptance criteria is a limitation on amplitudes at the machine. This limit is established to assure the design life of the machine and to prevent unanticipated shutdowns for maintenance. Measurement locations on the machine are at bearing housings and at base plate connections. Amplitude limits are usually from the machine supplier or project specification. The figure on the right is a sample from published generic criteria. The third acceptance criteria is human perception and tolerance to vibrations. This is a personnel health and safety issue, specifically for areas of the module that are frequently occupied by plant personnel. Human tolerance to vibrations is a function of frequency, amplitude, and duration of exposure. The chart on the slide indicates this relationship. The horizontal axis is frequency, the vertical axis is acceleration amplitude, and each plotted dark line is a duration. Acceptance criteria is usually not provided by the machine manufacturer. It can be taken from project specifications, Fluor's internal guideline, or recognized publications such as ACI 351-3R or ISO 2631-1 Annex B. Now it's time to summarize our discussion with the 4 points shown. Machinery modularization advantages include cost through a transfer of labor from field to shop, quality by using shop facilities and shop quality control, schedule by implementing shop and field activities in parallel, and by a reduction of weather delays. The listed feasibility study key drivers, in addition to those shown, indicate considerations of transportation logistics, the overall module arrangement, and individual module layouts. Modularized machinery string interactions include arrangement of machine and auxiliaries, performance requirements to assure reliability, and a dynamic analysis to validate compliance. Module structural analysis considerations include the same site design criteria as used for stick-built, transportation design criteria including design margins, and available internal efficiency procedures. I will now turn the presentation over to Nitin for some final comments.
Thank you, Bill. Fluor's machinery modularization methods are successfully implemented on several projects. It is worth stating that our engineering requirements for mounting machinery on steel surfaces are stringent and no less than those for installation on conventional concrete foundation. Some examples of modularized rotating equipment on Fluor and Fluor joint venture projects are cited on the next slide. As shown on this slide, different types of rotating equipment with small to very large installed power are mounted on transportable structural steel modules. Pumps represent about 80% of rotating equipment in most process facilities. In addition to the BB2 type included in the table, Fluor has also modularized API 610 type OH2, OH3, BB3, and ASME B73.1 pumps and motors, including adjustable frequency drives in various services on hydrocarbon processing and oil and gas projects. I will now hand the presentation over to Marcus.
Thank you, Nitin, and also Bill, for your presentation. We have several questions. So before we take the questions, I'll remind the audience that you can submit questions to the Q&A panel. Please address them to all panelists. So let's start with questions. Nitin, I have one. I'll start with you. When should equipment vendors be notified about the intention to locate their equipment within the module?
Yeah, the equipment vendor should be contacted as soon as the modularization concept is accepted for implementation. And we have to engage the vendors at that time to facilitate advanced engineering and exchange of technical information, such as rotor's balance quality, base plate design and mounting requirements, and civil data such as soil properties, stiffness, and damping. So the work starts at the time the modularization concept is approved, and it sets in motion the interaction with the vendors.
Great, thanks. Let's see, next question. This one is in reference to slide 26. I'll perhaps hand this one to Bill. Bill, can you elaborate on the design margins and why these are needed?
Okay, we've had experience on projects designing modules and tracking the weight report. And of course, the weight report is usually issued monthly and updates occur. And because the steel is pretty early in the design, we want to add a design margin early on to account for either weight or center of gravity changes as the design progresses. These margins tend to decrease as the design matures, and so we've kind of documented that the margins suggested for use. That's in terms of weight, center of gravity, and also module position on the vessel deck. and even utilization ratios are also included.
Thanks, Bill. The next question is in regard to the reduction in quantities. I believe this is on slide 9. I think this is a question perhaps for both. I'll start with you, Nitin, and then perhaps we can get Bill to comment as well. But the mention was that modularization allows for a reduction in material quantities. Can you expand and perhaps provide examples of what material could be reduced?
Yeah, the major reduction in the material is the saving in concrete. So that's just one example that there is a significant amount of the cost saving and material saving by eliminating need for concrete foundations for machines that can be modularized, and also for complex machinery strings such as gas turbine or steam turbine driven compressors, which also come up with several auxiliaries which are otherwise mounted on their own concrete mat foundations. All of these items and the auxiliary systems, when they are installed on a machinery module, the arrangement becomes very compact. All piping, cabling, and auxiliaries are connected, tested on module, and that is another saving in terms of the cost of investment. So these are just two bigger examples that I can cite.
Okay. Bill, perhaps you can elaborate on either reduction in quantities or maybe other impacts to quantities on the structural side.
Well, concrete is definitely reduced because we're taking a lot of items off of concrete foundations and putting them into modules. Of course, the quantities are probably going to increase because we're building more structures to accommodate the same equipment. Of course, the major savings also in doing all of this is there's a huge impact from the labor cost, as Nitin has mentioned.
Okay. Thanks, Bill. Bill, one more, next question perhaps is for you here. What factors play a key role during sea transportation which cause alignment issues and/or deviations during final installation? How are these factors addressed during the engineering stage?
Well, this may be a little bit more for Nitin than myself. However, that some disconnections are made prior to departure. I believe machinery usually undergoes a preliminary alignment in the module yard and a final alignment in the field, and some items are disconnected for transportation purposes.
Okay. Nitin, any maybe follow-up comments to that one?
Yeah, I will give an example of a machinery string that involves a centrifugal pump driven by an electric motor. A simple example as that, and the principle or the approach can be equally adopted for larger machinery strings. So for the sake of transportation, it is a common practice that the on module initial alignment is checked. The purpose of doing initial alignment of the machinery string is to confirm that the target alignment in the field can be achieved. In the field, we do the cold alignment and then followed by final alignment. Prior to transportation, the coupling hubs spacers are removed, but hubs are installed on the shaft ends and they are left as is, and only the coupling spacers are removed to eliminate stresses on the coupling during transportation, if any, as a result of impact loads or acceleration loads. And then the coupling, and also based on project specification or client requirements, it is customary to disconnect the first spool, suction and discharge spool on the pump. These are the breakout spools, and they will be reconnected at job site after the model is installed. The third is as an example of mechanical seal installed on the pump. Many pumps have facility to, or mechanical designs have seal setting devices, so the seals can be kept engaged with the locking device, so that prevents the possibility for any damage to the seal during transportation. And the fourth one is, if possible, the rotors are blocked from moving during transportation on land or on ocean. So these are some of the examples of measures that are taken to avoid possibility or to preclude possibility of damage to the machinery string.
Okay, thanks, Nitin. That was a good answer. Nitin, here, one more question for you. Does the spare parts philosophy differ for equipment based on whether it's installed in a stick-built or in a modularized structure?
The spare part philosophy does not change regardless of the location of installation, whether the machinery string is on concrete foundation or on module, because machines are built to the same quality based on industry standards and client or project specifications. In the case of API machinery, if it is a API 617 centrifugal compressor, the major capital spare parts or startup commissioning spare parts that we will specify will not be different from those if the machine is going to be installed on a concrete foundation or on a structural steel surface. Because we are looking at the duration of transportation here, whether if the module is transported on by land and then installed at site, or if the module is transported by ocean, then on land and then installed at site. We are looking at a differential duration which is not very significant, and that should not impact or affect the decision-making process regarding spare parts.
Okay, thanks, Nitin. Nitin, one more question for you, or the next question for you. Are there any specific types of equipment which cannot be modularized? And if so, what are the major drivers in determining whether this can or can't be done?
Yeah, as I've explained in the first part of this presentation, that the modularization study, which involves what can be modularized, what cannot be modularized, is based on several aspects which we evaluate during the concept assessment. To give an example of what type of equipment cannot be modularized, I will cite vertically suspended diffuser type pumps. These are the sump pumps and the turbine pumps that cannot be modularized, or they are not modularized because modules do not have integrated sumps or pits. These are the API 610 VS1 through VS7 type pumps.
Okay, thanks, Nitin. Next question, Bill. This one's probably more appropriate for you. Is concrete required for machinery supported in modules to provide the appropriate mass or ratio dampening for, mass ratio dampening for support of the machines?
This is something that's evaluated in the dynamic analysis. We have, I can think of one instance already where we did add some concrete to help supplement the dynamic response. It's normally something that we would try to avoid because we prefer not to transport the weight of concrete. And so it's usually added at the job site after we build a pan for it in the shop. It can be done and it will be done if it's shown to be necessary.
Okay, great, thanks, Bill. Next question is perhaps for both of you. Maybe I'll ask Nitin to go first and Bill can follow up. With the decreased congestion at site, is there a presumed positive impact on site safety?
No, because the modularization conceptual study will give equal weightage to the layout of the equipment on the string, but at the same time, look at human factors and accessibility and operability and maintainability. So there is no compromise whatsoever, regardless of the compactness of the module or the plot size on which the module is going to be built and installed. The arrangement of the equipment on the base plate, to give an example, on a conventional concrete foundation, if we are looking at a API 617 centrifugal compressor steam turbine driven train, there is a separate concrete foundation for the machinery string, and the lube oil console is mounted on the grade level because of the API 614 requirement for half-inch per foot slope requirement for the oil drains. In the case of modularized machinery string, the same string installed on a transportable steel structure usually will have the base plate installed equipment, which is the driver and the driven, and the lube oil console is usually mounted in a recess in the module's floor to allow the natural gravity drain from lube oil drain lines into the lube oil reservoir. So the arrangement is made compact, but that does not compromise operability, maintainability, and access requirements.
Okay, thanks, Nitin. Bill, any additional comments to add?
Well, I guess my thoughts are around the construction process. The congested sites, you have to address carefully the sequence of installation of the modules and how they get into the foundation. I have been on projects where we used flush base plates, and that allows more flexibility to maneuver modules into position. But most of the compressed size is dealt with in the shop with a smaller compressed module.
Okay, great, good answers. Next question, Nitin, I'll give this one over to you. How many rotating equipment projects has Fluor modularized?
Yeah, without putting up a number, I would say that Fluor has modularized many rotating and reciprocating equipment services on hydrocarbon processing, utilities, gas transmission, and oil and gas facilities, as cited on the slide that we had shown as examples of projects where we have machinery from large to small installed power being on the transportable steel structures. So we have the experience in modularizing dynamic and positive displacement type machinery. Also, there are some challenging services such as some of the pumps that we have modularized. They have been operating at service temperatures which are close to their fluid's auto ignition temperature. And some pumps handle very highly volatile hydrocarbon liquids. So we have to take special measures or special features were introduced in the design of these models.
Okay, thanks, Nitin. Next question, Bill. I think this one's probably more appropriate for you. From your experience, do ISO codes ever have requirements conflicting with, say, the DVN requirements?
Well, I can't say that I've run through both and done a line-by-line comparison. We'll typically choose to use one or the other, not both at the same time. I haven't seen anything, obviously they're written differently, and they both express similar concepts, but I hadn't seen any significant conflicts.
Okay. Bill, maybe next question, I'll continue with you here on this one. How are the modules typically fixed or affixed to the transportation vessels? How are the vessel loads applied to the modules?
How are they fixed, or how are the loads applied? Or is the question about both?
I guess it's two parts. Yeah, how are the vessel loads applied to the modules? I guess this is intended during transport.
Okay, well, the module is fixed to the marine vessel through the sea fastening. The sea fastening connects the module down to the deck, and the sea fastening is usually welded to the deck of the module. So that transmits the loads from the module down into or to the deck itself. An analysis usually by the marine contractor or naval architect is concerned with the deck and how those loads are transmitted within the vessel. The forces that are applied to the module during transport, of course, I've mentioned, there's the wave accelerations, the rocking and translations of the vessel as it travels across the ocean, and also the flexing of the deck itself. Of course, all of those forces, the flexing, of course, is transmitted through the sea fastening. The accelerations is transmitted directly into the mass of the structure. So it's forces that are computed by the naval architect, or in some cases the marine contractor, and we design using those forces.
Okay, thanks, Bill. It looks like we're going to have more questions than we're going to have time to answer. So to maintain everyone's schedule here, I think what we'll do is we'll move on, and I'll go into a little bit more detail on how we'll address the balance of the questions. We'll be hosting our next webinar on Thursday, October 15th at 10 a.m. Central Time, where Fluor subject matter experts Kevin Chase and Grant Anderson will discuss Fluor's Coker experience and industry-leading innovations, as well as share examples that showcase the magnitude and complexity of these types of projects. Please keep in touch with your Fluor contacts, follow our social media postings, or head to the Innovation Builders page on fluor.com to register for future webinars. We appreciate your attention and thank you again for dialing in today. We will send out a compiled list of all the questions and answers, including the ones we're not able to get to within the next couple days. We will also notify you when a recording of this webinar is available on fluor.com. If you have any questions or require additional information, please email innovation.builders@fluor.com and someone from our team will get back to you. From all of us on the Innovation Builders team, have a safe day.